Good morning. Welcome to this seminar organized by the project StoRIES, where we are going to talk about thermal storage, the materials used for this technology, and also a bit about the applications and how these materials influence the way the applications are considered. So a bit about me. I'm Professor Luisa Cabeza. I work at the University of Lleida, where I had a research group, GREIA, which is well known for working on thermal storage, because we started to do so in 1999. I always say that I love my job, and that's why I'm so passionate about what I'm doing. Lleida, it's a small city located near Barcelona in Spain, and we have a small university there, but still it reflects the size. It's about 1/10 of the population in Lleida, so therefore we have what it's called a university city with a lot of stamina inside for the researchers working there. Our research group work mostly on energy, of course, but we also have a big bunch of academics and researchers working on artificial intelligence that we also apply this to thermal energy storage and also on chemical engineering, which is where most of the materials research is carried out. The image you have in front of you reflects our DNI. We love being in the university and having these crazy ideas and see if they work in the lab. But also, since most of us are engineers, we love working with industry and trying that our ideas or our research, our work also has an impact in the day-to-day work of industry and of the society. These are our capabilities. I don't want to go in detail here, but you can see that we do a lot of things. And although we also look at other applications, thermal energy storage, it's been always our main drive. So let's start with the presentation itself. I will talk a bit about thermal storage and their technologies, and then the role of this technology in the energy system, because I think it's very important to understand how this impacts, and as I said, how the materials need to always take into consideration this application side. And at the end, if we have time, a bit about sustainability and social aspects, both of them, but especially sustainability, again, it's very much related to the materials. So we need to think a bit about the energy system. We need to remember that the energy system has like three main sides of it. It's the production, where we produce the energy carriers that we will use later. And here is where renewables are starting to have a big role, trying to substitute the fossil fuels that by excellence has been oil, coal, and gas. Then we have the distribution and transmission side of our energy system, which is where we transport this energy that we produce somewhere to the demand side, which is where our final users are. And here we have to remember that it's not only electricity that we are going to use at the end. We also have the heating and the cooling, and we also, of course, sometimes use directly the gas or even the oil. As we will see later again, storage has its role in the three sides. And thermal energy storage has its role in the three parts. But the technologies and the way you are going to implement this technology, it's very different. Usually when we talk in the production side, the storage will be bigger in size, and therefore the materials you need to use there maybe are very different to those that are used in the demand side, where maybe my thermal energy storage is much smaller because I have to put it at home. We all know about this. I'm going to go quickly, but all of these technologies on energy storage and also thermal energy storage is being pushed very much to our energy transition towards renewables, and the problem they have that they are intermittent. Also, we need to remember about all our targets that we have in Europe, but also worldwide. The Energy Green Deal is just one example developed in Europe, but I think a lot of countries all over the world are also going into this decarbonization of our system and also of the energy system. And again, if you read here, what are the goals of this again, being the Energy Green Deal, just an example, it talks about secure and affordable energy supply, but it also talks about energy efficiency. It talks about energy performance of buildings, and therefore behind it, and that's why it's called Green Deal, there is all this concept of sustainability that, again, we need to consider when we work with our materials. This image shows you this transition that we want to do. And again, as I said before, the main disadvantage of these new energy sources that we want to use, which are renewables, is that they are intermittent and discontinuous. And that's why thermal energy storage comes into place. But as you will see, it's not only, this is not the only application of thermal energy storage, of course. So what is in fact thermal energy storage? I would say that thermal energy storage is what we are more and more using, a heat battery. So it's a battery where instead of electricity, what I save there, it's heating or cooling. It's heat or cold. So it's thermal energy. The individual technologies, as I said, can use in different steps. But they also can be used in different temperatures. That's what we all think, since we are starting to talk about thermal, we think about temperatures, and then we talk about low temperature, medium, and high. Of course, what we would call low, medium, and high depends a lot on the application. So in a building, high temperature is around 120 degrees C. But if I'm thinking about an industry, high temperatures can be as high as 1000 degrees C. Also, thermal energy storage has an impact in the time that I store this energy. And this is where concepts like seasonal storage appear. So maybe in my building, I will save the solar energy from the day to be able to have a shower late in the evening or early in the morning. That's short term, daily. But it could also happen that in my building, what I want to do is to store the energy, the solar energy from summer for the heating in winter. And this is what we know as seasonal storage, which would entail weeks or months of storage. As you can imagine, the technology and the material used in these applications are completely different. Another very important principle of thermal energy storage, as in any other storage concept, is that you need to remember that you need to supply this energy into your storage and remove it. Okay, and here is where it comes the concept of power. How fast can I save this energy? So how fast can I charge my tank? Therefore, how fast can I charge my material? And how fast I can discharge it. And this is what we are showing here. And I always say that when we talk about materials, we remember only about the middle part in the storing, where really the storage material is, and where, of course, the selection of this storage material is very important. It also is what it gives my energy density. The energy density is how much energy I can store in my tank. It's related to the material itself. It's related to the properties of the material itself. We will see which properties later. But remember again that you need to charge and discharge this material. And how fast you can do that is what it gives you the power of this system. in some applications, like in a shower, in a domestic hot water, power is very important. When I go to the shower and I open my hot water, I want to have hot water immediately. While in other applications, for example, in a building, if I put my material in the walls to just keep the room at a constant temperature, there I don't want power. There I like that the material stores and releases the energy slowly. Okay, so that also, again, when I select my material and when I develop my material and when I write the requirements of my material, it cannot be done in a general way. You need to always think about which will be the application of this material at the end. Why thermal energy storage? There are other energy storage technologies. There are other energy technologies in general. But thermal energy storage has some benefits that make them very attractive for engineers and for all of us. One of the known benefits is that you can increase the generation capacity of a system without really changing the system itself. Because if you are able to generate more energy and save it to use it later, maybe because there is a mismatch between the time of the energy supply and demand, with storage, you increase your generation capacity without even changing your generation or your demand side of the system. The better operation of cogeneration plants, it's a well-known benefit, but I think that it can be, or it should be extended to most of other energy plants. Having a storage can help you maybe in modulating the energy temperature, modulating the energy supply or demand, and it really helps in the better operation of energy plants in general. Okay. Another very well-known advantage of thermal storage is the shift between energy purchased at the cost periods. An example is if I need to produce cooling with a compressor, that means buying electricity. If I do it when I need the cooling, for example, in a building, which is during the day, maybe it's when the electricity is more expensive. There are areas in the world where electricity is cheaper at night, for example. So one very well-known application of thermal energy storage is to use the cheap electricity at night to produce cooling, save it, and then reuse it during the day. How we save it? Known example, it's producing ice. So this is also thermal energy storage. This is the one that I was talking about, this peak shift, where I change this demand from one time to the next one. This also means, if you look in the figure that we have in front of us, that maybe I can reduce the size of my producing equipment, because if my cooling power, instead of being in 2 hours, which the power is very high, I can produce it during more time in other times of the day, it means that I can have an equipment with less power, I use it with more time, and therefore that means that not only the operation cost will be lower because I use electricity at a lower on another time of the day, but also the investment costs are lower. So we don't reduce only the OPEX, but we also reduce the CAPEX. So if now we are convinced that this is a technology that can help us, let's go to the technologies of them. There are 3 technologies in thermal energy storage, and they are actually very different in how they work, materials they use. Some of them can be used in the same application, but not always, and especially the use they have. So the most known one is sensible thermal energy storage. Here is where we just heat up a material to save heating. You can do the same cooling. And therefore, the amount of energy that I can save is completely related to two parameters. One is a property of the material, which is the specific heat. That's the energy that a material needs to be heat up for 1 degree C, and the delta T. In this case, the higher the temperature difference between the beginning and the end, the higher the amount of energy I will save. As you may know, the most known example, it's heating water, so water tanks, domestic hot water tanks. But today, it's also technology used commercially, for example, in concentrated solar power plants with this technology called molten salts, where what we are heating is not water, but we are heating a mix of salts that undergo higher temperature change, for example, from 200 to 500 degrees C. This is also starting to be used in industry, as we will see later. So as you can see here, we're starting to talk about very different materials and the way they behave. One thing is to heat water, and the other thing is to heat and cool a salt. Of course, you can also work with sensible with solid materials. You can heat up bricks, you can heat up concrete, for example. You can heat up any solid and also cool it down to be used. The second technology is latent thermal energy storage. In this case, in the latent part, it's where I use the phase change of a material to store the energy. It could be any phase change from liquid to gas, from solid to liquid. Usually in thermal storage, we use from solid to liquid because the phase change from liquid to gas means a volume change, which brings a huge challenge from the engineering point of view. That doesn't mean that it cannot be used, okay? That's why it's usually not looked at, okay? So usually we use from, as I said, from solid to liquid. The easiest example, it's ice. That's been used forever. We all know that if we put a piece of glass in our drink, it will stay cold longer. And it's because the ice has this very high energy density. Look at our figure here in the middle, and we will understand two things important. First, when we are using this latent energy, the temperature change in the material doesn't exist. So a material, when it melts or solidifies, it does it at constant temperature. Of course, this is ideal. In a real application, there is some temperature change, but ideally, it would be at constant temperature. That means that for some applications, this is a very nice technology. One example was the one that I was telling you. If I want to put a material in the walls of my building to keep inside a constant temperature for thermal comfort, you see, constant temperature, thermal comfort, I look for a material with a constant temperature. Okay, so I work with latent thermal energy storage. Materials used for latent thermal energy storage are commonly known as phase change material. A lot of people ask me, so what materials are phase change materials? By definition, everything that goes under melting when it's heated up, it's a phase change material. So the only exception are those materials that when you heat them up, they burn. So usually things like wood, for example. But most materials eventually will go into this melting. It's just that they melt at a given temperature. And again, here, it brings you the second topic important here. This horizontal line, the temperature, it depends on the property of the material, nothing else, okay? So if I'm talking for an application where I want that the temperature is around 20, 23 degrees C, like this thermal comfort, I need to find a material that it melts at 20, 23. So I cannot use ice because ice melts at 0 degrees C. Okay, while if I'm talking about cooling, maybe ice is a very good material. If I want an application where I want this constant temperature, for example, because my turbine needs a constant temperature, then maybe I need to find a material that melts at 350 degrees C. And the third important part with latent that I want to highlight is these purple parts that you see. And this is because any thermal energy storage system that uses latent heat also is using sensible heat. Okay, your system will always have to heat up your material to a given temperature where it will melt, and then it will continue heating up the material when it's in liquid state. The temperature change that you use, it depends in your system and in your application, okay? But your material will always be involved here. If you are using the material, only, excuse me, within the range of constant temperature, that's also fine, but then you have to keep in mind that you are not using all the energy density of your system, okay? And that's something that we need to keep in mind. There is a difference between the energy density of my material, which is the theoretical potential, and what will be the energy density of your final system, which it entails how you are actually using the material and the system. It could be less if I'm only if I'm, not going into the limits of this horizontal line. It could be more if I'm going actually into adding some sensible in it. And finally, the third technology is what it's commonly known as thermochemical. I never liked this name, and that's I usually talk about sorption and chemical reactions. And why is that? It's because fundamentally both are similar, but from the point of view of the process that goes inside it, it's not the same. Okay, in sorption is a physical change, while in chemical reaction is a chemical change. But it's true that the concept is the same in both. The idea is that, for example, I have a material which is solid, which is here the A. I keep losing my pointer, sorry. Let me see if I find it again. Here. So I have the A, that in this example, it's a solid. It's a material that when I heat it up, it releases heat. No, sorry, it stores, so it takes heat, so it stores heat, and it transforms itself into another solid material, B, and it releases a gas, C. When I want, and then I have these two materials, these two chemicals, that when I want to get this heat back, this energy back, I join them. It can be as easy as this, or it can need some catalyst, which might be even a little bit of temperature. But the idea is that I have this energy back, going back to my initial material A, okay? An example of this could be, for example, a material that absorbs a lot of water. So silica gel with water, when it's humid, this would be my A, okay? And then when I take heat, so I heat it up, it will get me this dry silica gel and water in gas. One of the nice factors of this technology is that if I'm in fact using a solid and a gas at the end, I can separate these two products. These two could be chemicals or products or components. And then, meanwhile, B and C are separated. They will never join, and they will never lose any of this energy that it needed to be separated. So that's why usually this technology, it's seen as a very nice technology to be used for long-term storage, okay? So we'll go back to this later, but if you remember, I discussed about seasonal storage. I could do seasonal storage with sensible, latent, and thermochemical. From the point of view of the technology and the chemistry, it can be done. What is the problem? The problem is that if I take water and I heat it up to, for example, 80 degrees C from summer, and I want to keep it on winter, probably when I have my tank with hot water, when I go in winter to retrieve this heat, the tank is not at 80 degrees anymore. It doesn't matter how well I insulate this tank, there is always energy losses. Heat losses are there in real life, there are no adiabatic systems. So therefore, sensible energy or sensible technology can be used for seasonal, but we will also have heat losses, and it could be quite high, okay? With latent, it's a bit similar, okay? When I melt my product and it's in liquid, because it's hot, it will also have heat losses, maybe less, maybe more. Another problem with latent for seasonal is the cost, but that's another topic. While theoretically, as we said in thermochemical, when I have separated the two products, either by sorption or by chemical reaction, in theory, this can be kept at room temperature without any energy losses, okay? So this is why this technology is more attractive for long term. Okay, another difference between the three technologies is the maturity of the three technologies, okay? Sensible is known as a very mature technology, although there is still a lot of research, for example, for high temperature storage, still a lot to be done, but we all know that molten salts are commercial, although still there is a lot of research to look for other materials. And water storage is also mature, although again, there is still a lot of research for example, decreasing the energy losses or other problems. Latent energy storage is seen of less mature technology, although there is some maturity need. You can buy PCMs in the market, you can buy latent-based thermal storage systems in the market. So the maturity is there, although there is a lot of research still going on the system itself, on the design of the container, but also on the materials. There are no phase change material in all the desired temperatures, okay? Especially at high temperature, if you look at the literature, there are temperature gaps where there is not a PCM that works super well at that given temperature. So there is a lot to be done still in that. And thermochemical is the less mature technologies. There are some products based on this technology in the market, but still a lot to be done. Here, for me, from the material point of view, it's where I see, let's say, less availability. I see a lot of research being focused always in similar reactions or sorption-based systems. I know it's not easy to look for new ones, but I would say that here is where a big challenge is for researchers. Okay, this is what I said. I wanted to use that slide because it helps me in comparing, but here you have more detail about the sensible examples with solids and liquids, and the equation that we use to calculate the energy density of my storage. And here again, some examples, okay? Some examples which are commercial. In sensible, it's, for example, what it's called underground thermal energy storage, where we use the soil as a storage material to save our energy. Of course, here as researchers, from the material point from the material point of view, you could tell me, Luisa, there is not much to be done, but still there is a lot to be done in the wells that we do especially if instead of aquifers, we use boreholes, in the material of the borehole to achieve the best, again, heat transfer. So the power of charging and discharging from my huge storage system, which is the earth itself, to my heat transfer fluid, which is what will move this heat or cold from the storage to the application, which in this case is a building, but it could be other ones. Another known system for sensible is what it's called pit storage systems. Here actually are usually either water, or when we say pits, it's not only a big storage tank, but a big storage tank with gravel inside, so that the material is more dense and you avoid some of the problems of having only water. Here again, there are challenges in materials. If we only talk about water, for example, most of the systems have linens around them that I know there is a lot of research going on that to find the perfect linen, especially for impermeabilization, but also insulation in there. But if we also talk about gravel, then which gravel to use, which material to use as this gravel, do we have to clean it, can we use natural materials, should we use, for example, and here we start talking about sustainability, a waste material from any other application that can be used as this gravel in the pit. I already mentioned molten salts. This is an image of a commercial molten salt system for a concentrating solar power plant. We always have 2 tanks, and actually it's called molten salts because the salt is in liquid state, and the salts are moved from one tank, which is the cold tank, to another one to be heated up, and it goes to the first one when it's cooled down. That means when with a heat exchanger I extract this energy. Usually in this heat exchanger, steam is produced from water, and this steam is the one that is used in the turbines to produce the electricity in these concentrating solar power plants. Here there is a lot of research going on, because although this is a commercial system, always the same salts are being used today, which is what it's called solar salt, which is a mixture of sodium and potassium nitrate. But other salts are being considered, both to improve the energy efficiency, but mostly to increase the temperature of this storage, because the higher the temperature of the storage, the higher the temperature of the steam produced, and the better efficiency in the turbine side. And here there are a lot of challenges. When you go to higher temperatures, maybe nitrate-based salts are not good enough. We have to go to carbonates, chlorides, and this brings a lot of problems. Not only, but one of the biggest problems is corrosion. But I say not only, because also stability, it's a problem. And in solid, again, conceptually, for example, when my application is a building, I can use the building materials itself, even the concrete, as a storage. But going that's more or less mature. What it's not mature, and where is a lot of research to be done by us guys, is at high temperature. Today, one of the topics being studied is the use of concrete for high temperatures. That means developing new formulations, because concrete break down at temperatures higher than 400 degrees C. But also in the past, other materials like ceramics were studied, and they could also be considered for these high temperature applications. Domestic hot water tanks, but also cold water tanks. This is a really common example of sensible storage. Again, this is seen as a very mature technology, but I know that there is a lot of research, maybe not in the storage material itself because it's water, but yes, in the materials that are used in these tanks, still what materials to use to ensure durability and to lower the cost. And this is especially important in cooling. The lower the temperature, the more challenges. This is the same as going high, okay? When you work at 100 degrees C, you have challenges. When you work at 400 degrees C, the challenges are not 4 times at the temperature, maybe they are 40 times. When you work at 1000, it's even higher. When I go down, temperature is the same. Okay, you know that when we go in temperature, the materials start to get brittle. So it's not easy to find materials for containers for very low storage temperature, but also the storage material here. Okay, there is some commercial available caltrates used for sensible cooling, but to me, this is something that up to now has been a bit disregarded by researchers, and we need to go back there because cooling is becoming one of the big problems in our society because a lot of our energy use is now in becoming more and more in cooling and not so much in heating. What storage materials to use to substitute water or to go lower temperatures? That's something that there is little research done still. Again, changing to phase change. We are talking here about phase change materials. As I said, one of the advantages here is that the energy density of the material itself is higher. Usually it's known to be at least 3 or 4 times higher per volume than is of storage insensible, especially for a small delta T's, okay? And that's why a lot of times this technology is used for applications where you have small delta T's, for example, a thermal comfort, but not only. As we said, ice storage, it's mature, it's very much used. And here, one of the research topics in materials is using slurries. To me, slurries are a bit in the age because slurries by themselves, it's a heat transfer fluid because it's a material that you use to move cooling. Usually, for example, ice slurry is a water that has ice inside, so you can move it. But of course, if we have a material inside that it melts and solidifies, it's true that we're also saving energy. So it could also be thought as a storage material. We discussed about thermochemical. I don't want to go back here. And now I go a little bit on especially what research we have done at the University of Lleida at the material level, so that you can see how much research needs to be done and can be done when you work with thermal energy storage materials. Okay, you can work on developing new materials. As I said, in the 3 technologies, there is a need for new storage materials for different reasons and with different requirements. But it's true that new materials are needed. And not only new materials, but also adding, for example, additives into these materials to change the properties and to achieve these requirements. Examples of it is, for example, the use of graphite or other materials to increase the thermal conductivity, for example, of PCMs. Another example is adding fire retardants to a material. It could, again, be a PCM, for example, organic-based PCM that I want to put in a building. And I have to add fire retardants to fulfill the requirements of safety in my application. It could be the idea of encapsulation. I haven't said that, but when I use phase change materials, I said we use a material that undergoes from solid to liquid. If a material goes from solid to liquid, it needs to be encapsulated. It needs to be in a container because when it's liquid, if not, it will be leakage. In some properties, I can just use a big tank with a coil inside where the heat transfer fluid goes inside the coil. And my storage material is in the tank, usually in the shell, and it just undergoes solidification and melting. And this is what we call bulk. But a lot of the times, I want to put the material in my, for example, in my building material, in my walls. Then I can add it just mixing, but then I have the risk of leakage. And that's why we work a lot, and you can work a lot in nanoencapsulation, microencapsulation, or what it's called shape stabilized material, which is when I mix two materials, but I make sure that there is no leakage. This is usually done with polymers. Another big topic is material characterization. I have been saying that we need to characterize our materials to fulfill some requirements that come from my application. And of course, then all materials need to be characterized. For many years, we have been working not only of characterization of the materials, but with many other laboratories to develop the correct methods for this characterization. It's not the same to measure a material, a polymer that is used in plastic applications, for example, in a calorimetry, where, for example, they can use 10 kelvins per minute for heating and cooling this material. While when you use this material for thermal energy storage, we all know that our materials change phase, so they have a physical process inside that takes time. So then in our characterization, we need to take this into consideration. And then when we use the calorimeters, we should use much lower heating and cooling rates. We're talking about 1 Kelvin per minute. This that today maybe it's a standard by most of the researchers working in this, and I say most because still not everybody is using it. 15 years ago was not so clear, and we had to work a lot on developing these methods. This has been done by many researchers, but there's been a big part that was driven by some of the working groups of the International Energy Agency, TCP on energy storage. I said that there are also a lot of problems with corrosion. In a way, it's logical. If I'm saying that I need to have my material inside a container, if it's sensible heating and it's a salt that it's molten and it's at 400 degrees C, I need to ensure that this salt will not corrode my container material. This happens with PCMs, this happens with thermochemical. So there is a lot of work being on this compatibility tests that need to be done and need to be studied for each application and for each pair, storage material and container material. And of course, when you talk mostly in thermochemical, but not only, because in a way, but anyway, in thermochemical, reaction kinetics are also very important. So here you have some examples that we have done in the lab. For example, when I talk about bulk PCM, which means a phase change material that is not micro-encapsulated or nano-encapsulated, we have been working, as I said, in mixing it with graphite and many other products to increase the thermal conductivity. We have doped our PCM with fire retardants, as I said, to achieve fire requirements. Here, to me, there is still a lot of work to be done because it's not easy, and the amount of fire retardants you have to add to the PCM a lot of times is too high. Remember that when I have and PCM is just an example of an storage material, but when I have a PCM and I add an additive that doesn't melt at the temperature of the PCM, that means that I'm decreasing the energy density of this material. So if I have a PCM, and I add 50% of fire retardant or graphite, I'm losing 50% of the energy density, okay? And that's not what I want. So I need to get this change in the property with an addition of an additive with the lower quantity possible. Going higher than 3, 4, 5%, it has an impact on the energy density that has to be really considered. We have also doped PCMs with nanoparticles to achieve different objectives. To me, the main challenge of adding nanoparticles to any storage materials is ensuring that the nanoparticle will stay distributed in all the material. And especially when we talk about bulk materials. In the lab, we start working with very small quantities. But if you think of the final application, for sure you will have at least liters, if not cubic meters or tons of material. So to ensure that your nanoparticle is still distributed around all your tank, for me, it's a challenge. And it's a challenge which is more difficult to fulfill than the change of the property of the material itself. And then I also discussed on encapsulation. You have some examples. The first one is a microencapsulated PCM. The second one is a nano-encapsulated PCM. And the third one is this shape-stabilized PCM. Here, as you can see, at the end, I have like a material, which is a polymer. And what we've done here is to put the PCM distributed to give this energy density to this new polymer. But at the end, we call it shape stabilized because it's a material itself with a shape that when the PCM melts, it's not a liquid, still the same material with the same shape. Maybe it can be a bit softer. And here again, the challenge is to ensure that there is no leakage. We have also worked with sensible materials adding nanoparticles, again, trying to change the properties of it. Could be thermal conductivity, but could be stability. There are many objectives in that. You can do the same with thermochemical. One of the examples of developing new materials in our lab at the University of Lleida is a few years ago, we worked with the chemistry department where they were producing ionic liquids, and they asked us to see if they could be good PCMs because they saw that they were materials that they undertake like the solidification liquid phase change. And we measured them in the lab, and we were very impressed because we were able to produce some PCMs that had very, very, very high melting enthalpy. And when I say very high, it's 4, 5 to 10 times higher than what is a normal PCM. Why is this not being further developed? It's because to produce these materials today, it's very expensive. But I still think that this is a niche of research because I always say that research should do things to be ready so that when the market needs this technology, this material, we are there ready. In the characterization, as you can imagine, we work a lot with thermal analysis. This is an image of our DSC. There are different DSCs can be used for characterization of storage of thermal storage materials, not only this one, which is a technique, but this is one of them that we use. And we work in developing the best technology or methodology to do this characterization. But this equipment that you see in this photo, which is kind of a box, this was a homemade equipment that we developed also a few years ago. And the idea here was that when we were working with our calorimeter, the calorimeter we use is this type of calorimeters that it's a heat flux calorimeter, and it uses only milligrams of material. And then when you are mixing PCMs with, for example, building materials like gypsum, concrete, it's very difficult to sample these milligrams of material and to ensure that you know exactly how much PCM is in there. So we wanted to go to bigger pieces of material to be characterized. And I'm doing this with my hands because this is more or less the size we were looking, 10 by 10 or 15 by 15 with 3 centimeters thickness too. And we developed this box that we call test box, where we can put our sample in the middle. We have heat flux sensors, and with these coils in the bottom and in the top of this we can produce the required temperature difference so that we produce a heat flux. This box is super well equipped with vacuum panels, 2 or 3 layers of them, to ensure that it's nearly adiabatic so that we have only unidirectional heat flux. The equipment in the right, it's a commercial thermal cycler used in medicine usually, that we discovered by chance, and we use today to thermally cycle, for example, our PCMs. The challenge here, or the restriction here, is that this only heats up to 80 degrees C, because of course was developed for medicine, which is their maximum temperature. But for example, for building applications or even for cooling, it works. We do a lot of corrosion testing. We do this by immersion testing. In the bottom, it's an example of a setup that we developed once that we wanted to do corrosion under vacuum conditions. Even though we think that there is no corrosion under vacuum conditions, there is, because again, since in reality, there is no perfect adiabatic system. So in the reality, there is no the perfect vacuum system. So you will always have some oxygen in there unless you use an inert gas. And we did some tests also under vacuum testing with this equipment, which was very interesting. And also we do mechanical properties at small scale and big scale, depending on what we are developing. Another type of testing is charging and discharging tests. And we do this usually with different forms of heat exchangers that you can see here. These are all shell and tube heat exchangers, but as you can see, some of them are rectangular, some of them are cylindrical. And here it's where we test our materials to see how they behave in a real thermal energy storage system. In this case, all is latent phase change materials, but we also do this with sensible, not so much with thermochemical. And for us, it's very important to do this because the behavior of the different materials is very different. It's very different if you work with an organic material than if you work with an inorganic material, which would be a salt hydrate or a salt. And then here we test different designs of our heat exchangers. As I said, these are all shell and tube, but we have tested other ones. But for example, here we were testing different fins to see how the system behave and if we can improve this charging and discharging power, because in some applications we need it. So let's change a bit about the topic. And I want to go back again to the role of this energy storage in the energy system, because now that we know the technologies and the materials that can be used, we can see where can it be used in the different areas of the energy system. This part of the presentation, I prepared it a few years ago based on different energy storage roadmaps that appeared in the literature. Most of them are about 10 years old today. A couple have appeared recently, but that doesn't change the overall concept of what I want to say. So energy storage in general, not only thermal storage, usually it's used for balancing demand and supply. We have seen this. Sometimes you have available energy production, like in solar, which is different in time to the demand. Okay, so when I need it to have my shower. When we talk about balancing, remember that it's not only about time, as I said now, it also matters, for example, at different temperatures. Sometimes I have surplus energy and low temperature and I need it a bit higher temperature. Storage can help here also. You need probably heat pump to increase the temperature of your energy, but with the storage, all of this system works better. You can also balance in power, as we already said. I have the energy at very low power, so I go slowly. And then I needed a big power, so I discharge fast, okay? And the last way of balancing is by location, okay? I can have the energy here. I can put transport the energy to another location. You can do that with a heat transfer fluid, but you can do that also with the storage. For example, charging and store. It can be a water store, difficult transport. It can be a PCM store. It can be a thermochemical, for example, with zeolites. And I put it in a lorry and I transport to another place where I use the energy. We can use it for managing the transmission and distribution grids. We will see how to do that later. Promoting demand side management. That means I need to make sure that when I use my energy, it's done in an optimized way, depending a lot on the supply and not only using it when the supply is available, okay? And contributing to the competitive and secure electricity supply, this is by adding renewables. So when we have this, I already have been telling you where can thermal energy storage can contribute. And this comes from the IEA Energy Storage Technology Roadmap that was done a few years ago, where they have this figure, and where I can highlight that already at that time, they understood that thermal storage can be used in the supply side, in cogeneration plants or in other power plants, in CSP plants, as we discussed with the molten salts, and it can be used in the demand side. We already discussed about underground thermal storage, cold water tanks, or ice storage tanks. You see, not all technologies are here, because not all technologies are mature enough that these roadmaps may catch them up and put in the system. But when I have a molten salt system, I can probably also have a thermochemical system when it's already available. And that's why I'm talking about the maturity of the energy storage technologies and highlighting again the thermal storage. And as you can see, at that time, the IEA identified thermochemical as being still under development or in research. They, at that time, identified molten salt and ice storage to being in demonstration and deployment. I always say that I don't agree with that. Ice storage is commercial in many Asian countries for many years, but it's true that there is a lot that can be done on it. And I think that's why it was added in this demonstration and deployment area, similar to molten salts. I agree that with molten salt, again, it's commercial, totally commercial, so we could put it in the other left side, but it's true that new salts are needed, as I said, for other temperatures, and so there is a lot to be done. But again, also residential hot water is here. And why? How come residential hot water is here? It's because here you say residential hot water heaters with storage. Okay, so it's going a step beyond having a domestic hot water, traditional just with water, and maybe I can add power to heat there, or maybe I can really design it for longer term storage in a more efficient way. And at that time, only underground and so UTES, underground thermal storage, and pit storage was seen as commercial, totally commercial, maybe not needing the research and cold water storage. One of the biggest problems of thermal energy storage is that it's very difficult to quantify the installed capacity. If I ask any of you how many kilowatts, but mostly kilowatt hours of energy storage potential we have with batteries, it might take you some time, but I'm sure you can do it because batteries are a commercial product. So you need to know to go to a database where it tells you how many manufacturing plants are there producing batteries in the world and how many they produce. And I'm sure you can come up with this number pretty fast. If I ask you how many kilowatt hours of ice storage it's in the world, that would be much more challenging for you, because ice storage is not a product you buy in a shop. Usually it's a system that is designed by an engineer. Okay, so it's much, much more difficult to quantify the thermal air storage installed capacity than the electrical storage capacity, installed capacity, sorry. There has been different attempts to do that. The first one was in the IEA energy storage roadmap. There is another one that we did it in my group in 2022. We did another one before that, but it's always a big challenge. And that's why also it's very difficult to convince policymakers that this technology is in the market and that there is a lot of it already installed in the world, because for us it's very difficult to quantify this. But anyway, I hope that you see that thermal storage can be implemented in many applications in our energy system. We all understand that it's mostly a lot of times done custom made. So that's why it's also difficult to quantify the installed capacities and also to show how many examples we have in the world. Okay, but we also see that if I ask you now, even after 1 hour of talk, which are the right materials for our thermal storage application, unfortunately, the answer should be, it depends. Because as you have seen right now, even without going too much detail, is that it depends on the application where I want to put it at the end. And that's the main thing, okay? For each applications, there are different materials, but not all materials, okay? And this is, again, one of the challenges that when I talk about lithium batteries or electrical batteries, in lithium batteries, it's clear there is 1, 2, 3 materials in electrical batteries. In thermal energy storage, there are hundreds, if not thousands, of materials that could be used, and none of them, unfortunately, it's perfect. Okay, again, to me, one of the things, and if you guys join this seminar thinking about materials, see that I'm emphasizing a lot the concept of system, because we always need to develop our material thinking on the system and the final application of the end. If not, we will not be successful in developing something that is really useful. Well, this is one of my favorite slides in my talks, is that to me, thermal energy storage needs much more visibility. And that's why I'm always happy to contribute with seminars to explain better this technology that everybody knows about it. So now a bit about applications. I have to go a bit fast because we have not that much time, but I wanted to, again, give you like a scope of the applications, not from the side of the technology, but now we talk about the side of the application, and I will highlight which materials are used in each one with examples that we have done at the University of Lleida, so you can see how many applications are there and which materials we can use in each one. So in general, when we talk about applications for thermal storage, we divide them in building applications. I usually have talked about high temperature application. I think this should be changed by industrial applications because then applications for cooling would also be included. And then there are other applications that you will see. For me, these are fun. And also it's interesting to see that a lot of these are the ones which are really commercial today. So going fast to the building applications, I don't want to be into detail into giving a lecture on buildings, but when we talk about buildings, the building itself and its energy performance depends on a lot of things. The first one is the building itself. It's the shape of the building, the orientation of the building. And then the second thing, it's how we build this building. So the materials we use in the buildings and how we use these materials. Okay, so as you can see here, we already have a big challenge because there are many professionals and laborers that work in this, okay? One of the main uses of thermal energy storage in building applications is to increase the thermal inertia of the building. And I always say and emphasize, when you use thermal energy storage, either with sensible, for example, putting massive materials, concrete, in your wall, or when you add even phase change materials in your building, you are not increasing the insulation of the building. That's a mistake. What you increase is the thermal inertia, and there is a difference. Insulation stops the heat wave. Thermal inertia delays the heat wave, okay? So the idea is that if I'm in a building in summer or with warm weather, this effect of the warm weather, usually it's the sun, will get into my building, and so I will be hot inside. If I put a layer of a material that ensures or that helps that this heat wave doesn't come at noon or at 2 p.m. when the sun is there, but gets inside the building at 6 p.m., 7 p.m., this is thermal inertia. This is what we can get with PCMs. And this, for example, could be very good for offices where I'm usually there from 9 to 5. But maybe it's not such a good idea at home because actually at 6 p.m. is when I will go home for dinner, okay? So I don't say that PCMs are not good for residential buildings. I'm just saying that you have to think that since what you are changing in the building is the thermal inertia, you need to see which material to put there and how to put it so that really the effect is the one that you desire. Okay. In this aspect, in the University of Lleida, maybe around 12 or 13 years ago, we started to build what we call cubicles because they are small house-like or small buildings where we were testing different thermal storage concepts. This was the view. Unfortunately, this setup today is still there, but it's not working. But we could take data during 12 years. That doesn't mean that we don't do this anymore. We just do it in another setup. These cubicles, which were 3 meters by 3 meters by 3 meters, they are big enough that when you measure the temperature inside, you can extrapolate it to the temperature of a room, a normal room in a building. And they are small enough that they were not extremely expensive to build. In here, as you can see, all of them had an HVAC system. In most of them, this HVAC system was only used to have a constant temperature inside the building, so to produce energy demand in the building, because we were testing different construction systems and material and building materials. So as you can see here in the image, we have, as an example, adobe, but we could also have only concrete. We could have concrete. When I say only concrete, was only concrete, which is already a material which gives some sensible thermal storage. We were using concrete with microencapsulated PCM. We were using the system which is with bricks, the traditional Mediterranean building system, and then added macroencapsulated PCM. And then it's when we were using these small cubicles, and these bigger cubicles, we were using active systems, either with ventilated facades or between floors active systems. A little bit of detail here, going fast. As you see here, this is what I was telling you, different construction systems, adding PCM or trying to test the thermal inertia of the materials themselves. These are all massive systems. We didn't have lightweight systems at that time in this. And what we were trying to see here is where we added the microencapsulated PCM in the concrete. These were the very first we did. And this is where we were adding the macroencapsulated with this metal shape macroencapsulated systems that you see added as a layer in the system. And this is the measurements we did. This is the characteristics. All of this is published. All of this you can find in the literature. So I'm going fast. Heavily instrumented cubicles, of course. And this is what we were measuring. When you have a PCM, your indoors temperature changes compared with a building without PCM. So the blue line is the building without the PCM. The green line is the outdoors temperature. And what we were reaching in the red line is that, as you can see, first of all, there are these nearly horizontal lines, which is when the phase change material is melting. And that means that the temperature between the minimum and the maximum inside the building is lower. This is when we approach thermal comfort. And also there is a delay of the maximum temperature. So here I reach 34 degrees 3 hours later than when I don't have PCM. This is the thermal inertia effect that I was showing you. It's not only decreasing the peak temperature, it's also having a given temperature later in time. This is thermal inertia. Okay, of course, this is still not within thermal comfort values, but this is where we could, in the first time, you see this is in 2005, so it's nearly 20 years ago, that PCM really had a positive effect in a building just by adding it in the walls. Another thing is how I control this effect, which in passive system is difficult. And that's why, okay, here is where we reach the thermal comfort. But this is why, going fast, we went to active systems. In a passive system, you cannot control. It doesn't matter which material you put. I didn't say it because I was fast, but we were trying organic materials. In organic materials, all of them work well. They had different energy densities. You have to put different amount of material, but all of them work well. Another thing is the thermal stability. But if I want to really control and to have this effect, I have to go to active systems. There are different ways. At once, I will only discuss with a bit of detail this one, which is a double skin facade, but as you will see, we have tested others. In here, we put the phase change material. These white things that you see in this image are the same slabs, metal slabs where you have PCM inside, and we put it in the facade. Okay, we compared it to a reference system without this active facade. And then in here, we had some slabs that can open and close, and I can control where the air is moving in this facade and when. Okay, so this is the idea that you have in the bottom diagram. I can decide when it's very sunny and it's winter, it's very sunny. I let the heat go into this facade with a glass, which I also have very good capture. And then, because of the greenhouse effect, and then the PCM is melting. If I need this heating right now, I do what you see in the image. I take air from inside the building. I get it through the facade where it will get warm because the PCM is melting. And so I have like free heating, okay? If it's summer and I don't want this heat to go inside, what I should do is take the air from outside, it heats up, so it cools down the wall, and it rejects it to the outside, okay? So I really make sure that there is this insulation effect, that even though the wall gets hot, it doesn't get inside my building, but I accept it outside. And the storage side comes when I can heat this, and if I don't use it, I close, and for example, in summer, I wait until this heat is needed. You can do this with free cooling also, charging the PCM with another temperature during the night, if you have like cooler nights, and use it for refreshing during winter. Again, which materials can you use here as PCM? Any. You just have to find a material that it goes right in your temperatures. Usually for cooling, with free cooling, we were using PCMs around 18 degrees C in our weather. That also depends on your climate. And if we were using this mostly for heating, you could go with PCMs which go 28, 30 degrees C. If you want to use it for all year long, then you have to get to a compromise where you will not get the perfect temperature for both seasons, but a compromise, as I said. And then you can use again an organic PCM and inorganic PCM, different materials. Here, and I'm stopping in this slide, and you will see that I go fast in the next ones because this is what it's available in the presentation, which we can share it with you later if StoRIES thinks that's a good idea, is that here the main challenge was the control of this active system. So when do I open it? When do I close it? How do I know when I have energy available? So should I start thinking on what weather will I have next tomorrow? Will I have sun available to heat my building? If not, how can I use my storage to have better energy efficiency and heating or cooling system in my building? So control starts to be very important. So as you can see, in thermal storage is not only the material, the system now is starting to find importance in control. And if you see that I'm starting to talk about, oh, I need to know what is the weather tomorrow, then here is when we started to use artificial intelligence to help us into having this better control and to understand, to get a control that with data from predictions in weather, data from predictions in electricity, because here also we are using fans, so we're using electricity, and data from my measurements, and we want to have the less measurements needed possible, because in a real application you are not going to have these heavily instrumented houses, how my system can perform with the best way, so that all the work that I have done in developing the material, choosing the material, and putting in a perfect system, it works best. These are the type of graphs that we get. Again, here you see the phase change of the material with these green lines. And also you see the energy savings, okay? I will not go into detail here. Again, all of this is published, but because here again, we go very much into these needs of the control. Maybe this slide, I stop 30 seconds, because here is where we were trying to see, is it how important or how much needed is to find the correct PCM temperature. And when I say PCM temperature, at the end, it's the PCM material. And what would be the influence in the average net energy savings? And to have this figure that you see here, that again, it's published, we tested different materials for each climate and weather in the different locations that you see with the different dots. And in each one, we selected what our simulations taught us was the best temperature, put the properties of a commercial material on that properties, and then calculate this average energy savings. And we saw that, in fact, of course, if you have the PCM with the perfect melting temperature for your climate in that location, your average energy savings changes, and therefore your profitability increases. So again, this is one of the drawbacks of this technology, that it's not custom made. You cannot just say, okay, just use this PCM. I will tell you, where do you want to put it? And it depends very much on your weather. And of course, this was done with a standard weather for several cities, but you all know that the climate or the weather can be very different in a city which is next to the coast or only 150 kilometers inland. Okay, these are the savings. And this is the part that I told about you with control that we did with artificial intelligence. I don't want to be too much long here because we don't have too much time, and this has not a direct relation with the material, while the part on the sustainability, yes. So I want to spend a bit more time there. But these are all the tests that we did to see how artificial intelligence predicting climate and energy price can do better in having a better performance of our thermal energy storage system. In this case, was in a building. Okay, high temperature applications. There are some examples here. One is we did this in this pilot plan that we built in Lleida, also University of Lleida in 2009. And the idea here was to go to higher temperatures, but also to higher sizes, okay? And, okay, I will go more details later, but this is the pilot plan. You see the image in the back where we have a storage tank. Our storage tanks were for PCMs around 100 kilograms of PCM, and we also had 2 molten salts tanks with 1 ton of sensible molten salts, okay? The electrical boiler, it's the heating, it's my sun, it's my waste heat from the industry, okay? It's where I produce the energy supply. And this air heat exchanger, air heat transfer fluid heat exchanger, which is this box you have here in the right, is what it simulates my energy demand. So when I discharge my storage tank, I do through the demand that I can simulate in this heat exchanger. As you can see, we tested many materials, well, many, considering that this research is not only expensive, but time consuming. But we were testing different materials to be used as thermal energy storage, especially as PCM. And also maybe not much related to the storage site itself, but to me also related to materials that we also tested 2 different heat transfer fluids in the pilot plan. Let me see what my slide. Let me stop here one moment to discuss 5 minutes about materials. One of the very interesting things that we found when we were doing this test is that the materials not always behave the same when you are testing them with grams than when we are testing them with kilograms, okay? And this is something that I would like to highlight a lot. And I usually do when I talk to people working on materials. When we work with materials, we are used to do it in the lab with very small quantities. And when we talk about thermal energy storage, where a lot of the changes are actually physical changes, the materials behave differently when they are in big quantities. Okay, let me give you an example. An example was the test we were doing with the mannitol. When we were working with the mannitol in the lab, we found that we had 2 peaks in this material. And this is due to the crystallization with the phase arrangement of this material. And then my PhD student was doing the test in a tank like this one in the image, the one in the bottom, which he had 100 kilograms of the mannitol. And he found also 2 peaks, but one was at a different temperature than we were looking in the lab. Of course, the first thing when you see this, as an advisor, you tell him, something wrong, repeat the experiment. But we kept having the same behavior. And then one of the material science that I had at that time in the lab told me, Luisa, let's look in the literature. And we found out that the mannitol actually really had, depending on the behavior of the material, could have 3 different peaks at 3 different temperatures. And depending on how you heat and cool this material, you can have only 1 peak or 2 peaks, or even 3 peaks, okay? So what it happened is that the way we were heating and cooling this material in the lab, and when I say way, usually it's the heating and cooling rates, so how fast you do it, they were very different to what we were doing in the pilot plant, okay? So again, be careful when you work with materials, especially with PCMs, but not only. I've seen things strange also with sensible, because the materials have a different behavior. So I would say always that scaling up, it's very important, okay? Scaling up is a very typical concept in chemical engineering. When we are producing materials in the industry, we produce our synthetic route in the lab, and everybody knows that then you have to scale up. You have to slowly go up because there could be changes because of the heating and mass transfer, especially, but not only, your reaction time, your kinetics of the materials. But in thermal energy storage, this concept of scaling up was not so much. People thought, I do something in the lab, and then I take this material, and since there is no real chemical change, of course, the exception here is thermochemical, everything should be the same. No, that's not true. You can be using materials that they behave differently. Okay, I already discussed about the storage in CSP and how molten salts are used. Molten salts are used, as I said, in our pilot plant. You see, we have 2 tanks, which are exactly the same as they used in the molten salts plants, but instead of having 4, 5, 6,000 tons like they have in the industry, we have only 1 ton in our lab. And here we just see the pipes where we were transporting the molten salt from one tank to the other. This part in the right, it's the heat exchanger that was exchanging the heat with the heat transfer fluid coming from the tank. Here, we mostly used the solar salts, but here we were very much interested in testing the behavior of these solar salts, if there was any thermal degradation, if there was any problem with heating and cooling. And at that time, we helped the industry to develop this technology. We also used byproducts, okay? And since I'm running out of time, I don't know how much I will be able to go here, so I will use this slide to show you. This is just an example, but at that time, we were working with Chile, and in Chile, it's where they produce the nitrates that we were using in our plant, that we were using them, as you saw, only in sensible storage, but also we started to see if they could be a good PCM. And then the people working there told us, Luisa, in Chile, we have a problem, which is when we produce these nitrates for any application, we also produce in the production part, which is, as you can see here, this is the production, which is mainly by evaporation. There are also other salts, usually they are a mixture of salts that are produced. Some of them have good applications and we sell them, but some of them, and one example is bischofite, doesn't have a very good application. Bischofite is a material that today is used mostly as the icing salt. So these salts that we throw in the roads to avoid icing when it's very cold, a lot of times is bischofite, okay? And we started to look at this material, which is mainly magnesium chloride hexahydrate, which we knew it was, when it's pure, it's a good PCM, but bischofite is not a pure material. So can we use this as PCM without having to purify it? Because if we have to purify it, okay, then it's not bischofite anymore. It's not my byproduct. Okay, it's another material. And we characterized it, and then we tested it in our pilot plant. And you see the heating process and the charging and discharging. And we saw that the behavior was good. Maybe it doesn't have the same energy density as the magnesium chloride hexahydrate pure, of course, because as I told you at the beginning, if I have additives, that can be the additives or can be impurities, I will not have the same energy density. But since it's a byproduct, it's much cheaper than most of the salts that we buy and we consider. And then maybe even if I have to put more volume in my system, it doesn't matter because it's cheaper, okay? And this is where also I want to bring this issue to your attention in this seminar. When we think about materials for thermal energy storage, we should not always think about very pure materials. There are applications that need that. But a lot of times looking at byproducts of waste could be also a very good thing. And then the challenges are different. Here, my challenge is that, of course, the cost. I need to make sure that if I have to buy more tons, it's still cheaper than buying less tons, more expensive. And remember that if I buy more tons, not only I have to buy more tons, but my tank will be bigger, so will be more expensive, etc. Okay, so this is one challenge. But the second challenge from the material point of view is this material still okay from the point of view of corrosion, from the point of view of chemical stability? So maybe my storage material itself, like my magnesium chloride, is stable, but I have this impurity that under thermal cycles, which is what we have in our application, will degrade. And then if it degrades, maybe nothing happens, but maybe I have, I don't know, a gas. Maybe it's more corrosive. Maybe, you know, there are other challenges. So don't disregard this idea, but then really sit down and think what you need to test to make sure that this would be a good storage material. And when you find a challenge, like for example, the one that I said, okay, there is an impurity that I know that eventually will degrade and will produce a gas. Can I design my storage system in a way that I can get rid of this gas either by releasing it to the atmosphere or collecting it and then selling or disposing it, but still the system can work? So these things are something that we also should take into consideration also from the sustainability point of view. Just using new materials is not always a good idea. Let's try to use these byproducts. This is another example. We did work 10 years ago with this company. We are working again with them. This is Iberpotash is a company here in Catalonia producing mostly chloride, sodium chloride for eating. But ICL itself today, it's a bit worldwide company producing a lot of salts. And as you can imagine, they are interested in thermal energy storage from the point of view of using their salts, but mostly for the point of view was trying to use their byproducts. Okay, so we are working with them in seeing the potential of those things. This is one study that we did, and we were able to publish. Not everything that we do with industry can be published, but the idea and the concept, I wanted to bring it to you. Another one is we have been working also with concrete for sensible energy storage at high temperature. To do that, as I told you before, the biggest challenge is that if we use standard concrete with Portland cement, when you go higher than 400 degrees C, this storage collapses. This is why buildings collapse when there is a fire. So now our challenge is to produce a concrete that can withstand 700, 800, 1000 degrees C. We have been doing this for the last 5 years. There is some work published, which is what I have in front of me. We just submitted another paper with better performance. But again, here, the idea is that when we look at all the aggregates that we need to add to this concrete, to achieve the requirements that we want, which of course the main one is withstanding not only high temperature, but thermal cycles, which is also a challenge. Having high thermal conductivity so that I have a proper charging and discharging power. To achieve this, when we look at our additives, we always also test byproducts from the industry. Sometimes it's byproducts from the metallurgic industry, like steel slag. Sometimes are byproducts from the mining itself. Sometimes the same cement company we are working with tells us, where we have our aggregates, there are these materials which we cannot really use in our production. Can you see if you can use it in your production, in your concrete? And that's what we are working with. So again, at the University of Lleida, when we are developing new materials or new formulations, we always keep in mind the circularity and the sustainability in the developing of our materials. In the other applications, as I said, for me, it is always nice to have this slide. We worked with this in the past. We don't work on this, but here is just some examples of where, especially phase change materials are used commercially for other applications. And I'm sure you all have seen this, not always thinking or realizing that it's thermal energy storage. The clear one is this one in the right, these soft containers. This is something that, okay, this is just an example, but for example, when we have injuries in our knee, we have this pouch that we put in the freezer, and then we put it on top of our knee. Sometimes we use ice, but today there are these more sophisticated pouch. These are phase change materials. These are materials that what we are using is the melting solidification change in my application, which is medicine. In medicine, phase change materials are used a lot for transport of blood, but also vaccines. During COVID, there was a big development site because there was a need of a lot of transport of vaccines, and not everywhere you have refrigerated trucks, or also not everywhere it was the best way. So a lot of times phase change material is used in this transport of medical things, vaccines, medicines, blood, etc. The one in the left, what here it says all-purpose delivery transports. You know that in countries like US, where cities are big, the pizza delivery guys have these bags where they have PCM inside. I know that, for example, in Europe where I live, usually this transport, it's only insulated with insulation material because the transport time is smaller. But I know that in the US that sometimes the transport is longer. To ensure that your pizza arrives home warm or hot, they use PCM in these transport boxes. And another application that started with just PCM punches like the one that you have in the images is thermal management of batteries. And as you might know, today there is a lot of research on thermal management of batteries, and a lot of it includes the use of sensible cooling or with PCMs. And that's why I started to say that cooling is starting to be one of the research needs we have for batteries, for buildings, for industry. You see that most of the examples that I give that are more mature are for heating. We need to start thinking in cooling, and there are not so many materials that can be used for temperatures below atmospheric temperature. So that 10 degrees C, 0 degrees C, minus 10, but when I start thinking of minus 30, minus 50, which is really in an industrial need, and where there is a lot of energy used just to cool heat transfer fluids, and they are not using storage. And now I'm starting to have people contacting me, and I know that there are no materials, or there are not as many materials. So this is something that would need to be looked at. Okay, and then in the last 10-15 minutes, I will have a very short point of view about sustainability and social aspects, especially the sustainability, because I started to say this, but to me, we need to go beyond technology, we need to go beyond materials, and we need to always keep in mind all these social and environmental aspects of our technology. And that means changing a bit our mind and remembering that whatever we do today, it will affect our world, and it will affect the future of our planet. So this idea of, for example, using byproducts, as I started to mention before, it's very important. Well, these green roofs, I will go first, but for example, in this case that I show you, you saw this image in the right, in the bottom before, where I told you that we developed a shape stabilized material. But when we did this, we used a lot of byproducts. Behind the goal of this material, of course, was we wanted to have one, this is actually a polymer that wanted to substitute something that is in the market, that is used in the building industry for acoustic properties. So a lot of times in our buildings, they put these layers of a polymer that has a lot of density, but weight density, okay? So it's a polymer which inside has material which are very heavy in weight. And this is what it gives these acoustic properties to this material. So at that time, what we wanted to do is, why don't we try that this material also have thermal properties, okay? And again, we didn't go so much to thermal insulation. We went to thermal inertia, putting PCM in the material. So we did two things. First one is all the material that we will give it, to give it weight density, it will be something that has to come or be a byproduct or a waste from industry. And in this case, for example, the final material we chose, which is not the only one we tested, was an electric arc furnace dust. We characterized it. It's just a black, nasty product, very heavy in weight, and that's what we mixed in our polymer. And the second thing is that we would add PCM, and in this case, we went for what it's called bio-based PCM, okay? You may know that organic PCMs, they can be paraffins, but paraffins are oil-based PCM, so they are fossil fuel-based. And then there are esters and fatty acids and other materials, which are what is called bio-based PCM. Okay, so instead of using a paraffin here, we were using a bio-based PCM. And we produced this new material that we characterize a lot. Here again, talking about materials, there was a challenge on how to characterize this polymer. So you can take this polymer and take a small sample and put it in the DSC, but since the amount of PCM is small compared to the material itself, and the polymer would not go phase change in the temperatures we were testing, there was a challenge on how to use it, and we developed a full method with our DSC to be able to produce this figure that you see in the left bottom side. And then, as I said, we characterize it completely, not only from the thermal point of view, but also expansion coefficient, the mass, the acoustic insulation, always comparing it to a commercial material, which is this Texsound. And we even went to an industry and produced several square meters, so not only in the lab, but in a real industry. So we saw that we could scale up from the point of view of production. And then we tested it in our cubicles in this setup that we have. And here we put the material in the inner wall, internal wall, okay, you see. and we equipped the size where in a room we could change the temperature, so really controlling the different temperatures to day and night, and winter and summer. And in the right side, we had free floating, and it's where we were measuring the behavior, which is the figure you see in the bottom. Again, reference cubicle was a standard commercial membrane, and the PCM cubicle is our newly developed membrane with PCM in it. And we could see a difference. This is from the thermal point of view, and also, as you can see, we also measure, of course, the acoustic performance. Again, this is an example of going, this was actually a full PhD of one of my former students, but it was really going from the lab, selecting the materials, characterizing them, producing a new material, a new thermal energy storage material, a new material with thermal energy storage properties, doing the full characterization in the lab, then doing the scaling up in a company. We found a company that they could produce the material for us, and then testing it in a real, or not in a real, but in a already pilot plant experimental setup with a building to see what would be the performance outside of the lab. We have done similar issues when we use RAM earth. We tested to give more thermal inertia here, again, not with PCM, but with the RAM earth itself. It also gives thermal inertia. And then we tested different materials. In the top, it's different waste from the agriculture. Usually straw is what it's used, but we were also using corn plant and fescue. And in the bottom, it's really waste from industry. One is olive stones, which is what it's produced when it's a waste from producing oil, olive oil. Rubber crumbs, which is a waste from our tires, from the cars. And this polyurethane, it's actually a waste from recycling refrigerators. So all our refrigerators have an insulation around it, which is polyurethane based. And when they recycle it, this type of pellets is what they came from the recycling. Again, we tested it. We did this also in these cubicles. I don't want to go in detail, but here again, it's based on sensible performance, but trying to get also this thermal inertia effect in the building. Okay. This is very similar, but in this case, the waste we were using, which is the picture with this seagrass, this is waste from the sea. Okay, so this seagrass is this algae that end up in the beaches, and that the municipalities have to take out so that when we want to go to the beach to play a sunbath, the beaches are clean. Again, a waste that we were trying to add in our construction system to give this thermal inertia effect. We have used PCM in gypsum. In this case, we were using PCM and also lignin, which is another byproduct from the industry. In this case, is the biogas production industry. They have a lot of lignin. And we're mixing it with gypsum and with PCM to see the effect on the gypsum and what it would have in the buildings. Here, for example, one of the side effects of using lignin is that your gypsum is not white anymore. It becomes brownish. Okay, you can see this as a problem or a drawback. Okay, my gypsum is not white anymore. You can see this as, okay, but maybe in my walls, the gypsum, if it's a standard and it's a nice brown, is not a problem. And of course, you can always paint it, okay? Another is we have been working, this has been in the last 3 years, using waste from the textile industry, this case is in Tunisia, to add this in mortar with and without PCM. Here, of course, the waste from the textile industry, that at the end, it's a mixture of materials, it's not only cotton. It gives it insulation. Here, yes, I'm giving insulation to this new construction building material. And then we were seeing if it's worth to also add PCM, if the effect would be high enough that it's worth it and it's able to use. This was interesting for this PhD student. She was doing the PhD in Tunisia, but was doing the experiments in Lleida, because she was telling me that in Tunisia, a lot of poor people, they only build their buildings with mortar, not even with concrete. And because they are like, only one floor houses and they are poor and they don't insulate these buildings. So the idea was, okay, let's see if adding this textile waste from the industry, which again, it's cheap, it's probably a cheaper insulation material than what you buy standard, works well enough. And then with the PCM, we also wanted to know, okay, it's not that cheap, but let's see if it also the effect is good enough that then the country can invest in helping the people when they build their houses to use this PCM based with textile mortar to have a better performance in their buildings where they live and have a bit more of thermal comfort. And finally, and I will stop just after this, although there are some slides left, is what I already discussed with you with another example on materials. When we are developing new formulations for concrete, our aim here is around 700 degrees C up to now. Now, next challenge is 1000, is using byproducts from different sources, so that all the material used in our, or most of the material used in our new concrete is also sustainable and based on recycling and circularity. So that we not only have a new thermal energy storage material with a new concrete formulation and a new thermal energy storage system and application, because this challenge of storing at higher than 400, 500 degrees C is not only for concentrating solar power, for industrial applications, it's really a demand from the industry, but that what we provide them is also as sustainable as possible. We were trying to have something that would use as much as possible byproducts, and that then when its life is finished, it can be reused. And now we have to do tests with our own samples from the lab to see really if this new concrete is reused. When we smash it, we can produce either a new concrete or a new compound, which is based on this concrete that can again be used maybe in thermal energy storage. Okay, so again, when you think about materials for thermal energy storage, please keep in mind circularity. Try to use materials which are readily available, materials which are as much as possible sustainable, and especially also think that if it will be easy to recycle after use. And here, one example, which is not a good example, or is an example of not being this the case, is when we mix, for example, microencapsulated PCMs with gypsum. We are not going into the direction of circularity. I'm not saying this is a bad thing. I'm just saying that this is a reality and that we have to take into consideration. And with this, I will go fast to my last slide, because I think, sorry, I wanted to go fast and I went too fast, because as I said, all the work that I presented in this, it's published. I didn't add all the references because they are a long list of references, but please, if you reuse any of this, look at the source and reference it appropriately. I need to acknowledge all the funding that we got at the University of Lleida to do this research, but especially I want to thank StoRIES for bringing us the opportunity to have seminars like this and for inviting me to give this talk. And with this, I finish. Thank you very much.